In this video, we will introduce a new state variable that is called entropy. First, let's review what we said about state variables. We have seen that there are variables such as pressure, temperature, volume, the total mass, or the number of moles that can be used to characterize a state. And we have seen that there are relations between those state variables that are called equation of state. For example, we discussed the ideas gas law, PV equal nRT. And then we have introduced a new state variable, the internal energy, which is the sum of all the kinetic and potential energies of all the particles. And we have discussed also how it is related to other state variables. For example, for an ideal gas of monoatomic particles, U, the internal energy, is equal to 3/2 nRT or 3/2 PV. And for an ideal gas of diatomic molecules, it is 5/2 nRT if the degrees of freedom of vibrations are frozen, or 7/2 nRT if they are not frozen. Now, these state variables can be separated into two categories. If you double the system, some variables remain the same. Those are called intensive state variables. For example, the temperature or the pressure. And some variables are doubled when you double the system. For example, the volume, the total mass, the number of moles, or the internal energy. And so those are called extensive state variables. Now, we have also seen quantities that are not state variables. For example, the work done by the gas, or the quantity of heat that is added to the gas. These do not describe a state, but they describe a process, and they describe a path between two states. And we have seen that the first law of thermodynamics relates the change of a state variable, the internal energy, to the non-state variables W and Q. Now, for an infinitesimal step, we have seen that we can write the work as P dV. And we can do this if the difference in pressure that makes the piston move is infinitely small. Right? So at any step, the piston is in quasi-equilibrium. I mean that the pressure is almost the same on both sides of the piston, and so we can call this a quasi-static process. Now, using this relation, we have seen that you can calculate the work during a process as the area below a curve in a PV diagram, for example. And that's very convenient. Now, it would be nice if we could calculate the heat in the same way. We know that the work is the result of a pressure difference, and we know that heat transfer is the result of a temperature difference. So we can guess that the heat transfer will have the form of a T multiplied by a change of another variable. So here I write ds, and S is this new variable that we call entropy. Now, in a future, one of the next videos, we will see that S is a variable that represents the number of microstates of a given state. So S is a state variable. Now, since dq is equal to T ds, then we can calculate ds as dq over T. So let's discuss what this means for the entropy. Since dq is a quantity of energy in joules and T is the temperature in Kelvin, then the entropy has the units of joule per Kelvin. And we can also see that ds will have the same sign as dq, so ds will be positive for dq positive, and ds can be negative if dq is negative. For the total change of entropy between an initial and a final state, then we can use the integral of ds, and we can do this if the entire process is quasi-static. And if, in addition, the process is isothermal, we can take the temperature out of the integral, and we have delta S is equal to Q over T. If the process is adiabatic, then dq is equal to 0, and so the integral of 0 gives 0, and so delta S is 0 for an adiabatic process. And we call this also an isentropic process. Now, that's pretty much all you need to know. In the rest of this video, we will do a few examples where we calculate the change of entropy. So in the first example, let's imagine that we have a block of ice. And it is at a temperature of 0 degrees Celsius, and we add heat to the ice. Eventually, all the ice will melt, and you have liquid water at 0 degrees Celsius. Now, how much heat do you need to add for that? We have seen that you can calculate Q for a phase transition as the product of the mass multiplied by the latent heat. So here, we will use the latent heat of fusion. And what is the change of entropy? So this process is isothermal. So delta S is simply given by Q over T. And assuming that we have 1 kilogram of ice, for example, then it would be 1.22 kilojoule per Kelvin. Now, let's assume that we continue to add heat to this system. So eventually, the water will reach a temperature of 100 degrees Celsius. Now, during this process, the energy that is added can be calculated using dQ is equal to mc dt. And in this relation, C is the specific heat of liquid water. Now, this time, this process is not isothermal, right? The temperature is changing, so we will need to calculate the entropy change by the integral of dQ over T. And that will give us mc integral of dt over t, which is equal to mc times the log of t final over t initial. And so I will let you calculate this. Remember to use Kelvin for the temperatures, and then you find the entropy change. Now, let's do another example of question. What is the entropy change during the Carnot cycle? Well, you can answer this question even if you don't know anything about the Carnot cycle. Right? Remember that S is a state function, right? So it only depends on the state, not on the path. So if we have a cycle, the initial state and the final state are the same. So delta S is equal to 0. But we should also be able to find this if we add all of the delta S of each steps. So remember, the Carnot cycle has 2 isothermal quasi-static processes and 2 adiabatic quasi-static processes. So for the 2 isothermal processes, we can write delta S is equal to Q over T. So we have QH over T hot plus QC over T cold. Now the isothermal expansion, we have a positive delta S because QH is positive, and the isothermal compression will have a negative delta S because QC is negative. And in fact, we have seen that QC over QH is equal to minus T cold over T hot. And so combining these results, you see that delta S is equal to 0. Then for the 2 adiabatic processes, because dQ is 0, then we have delta S equal to 0. So indeed, you see that delta S total will be 0 for the entire cycle. Now let's do one more example. Let's say that you have a barrier that separates 2 volumes. There is a gas on the volume on the left and vacuum for the volume on the right. Then suddenly the barrier breaks or it is removed. Now the gas will move, and at the end it will occupy the 2 volumes. This process is a famous example. It is called the free expansion. So what do we know about this process? Well, there is no heat exchange with the outside, so Q is equal to 0. And then it becomes interesting when we consider the work done by the gas. Maybe you want to calculate the work using PdV because the volume is doubled. But what will you use for the pressure? You see that on one side we have the pressure of the gas, but on the other side we have vacuum. So the system is never in equilibrium during this expansion. It is in equilibrium at the beginning when the barrier is there. It is in equilibrium at the end but it is not in equilibrium in between because there is a difference of pressure. And so we cannot use dW equal to PdV. In fact, the gas is not pushing anything. We cannot use this to do any kind of mechanical work. And so the work is zero. There is no energy cost to move into vacuum. Then using the first law of thermodynamics, we have delta U equals 0. And if the gas is an ideal gas, since U depends only on temperature for an ideal gas, then delta T is 0. Now you see that the energy is the same before and after the expansion. So the first law of thermodynamics does not tell you anything about in which direction this process should happen. But we all know that this process only happens in one direction. Right? The gas will expand to occupy the whole volume. It is not possible that the gas molecules will all go back to one side and occupy only one half of the volume. But the first law doesn't explain this. The energy is the same in both situations. In fact, nothing you have learned so far in physics can explain this. We will see that this is a result of the second law of thermodynamics. So let's calculate the change of entropy during this process. Now, we cannot use the integral of dq over t because it is not a quasi-static process. But we can use the fact that S is a state function, and so it only depends on the state, not on the path. So we can go from the initial state to the final state using another process and calculate the entropy change for this process. And because S is a state function, then the entropy change will be the same. So we just mentioned that the temperature does not change. So we can assume an isothermal process. And we can choose it to be quasi-static so that we can calculate the entropy change. So for an isothermal process or on an ideal gas, we have seen that Q is equal to W, and W is equal to nRT ln of V final over V initial. And since V final is twice the initial volume, we can calculate that Q is equal to nRT ln of 2. Then we can calculate delta S for an isothermal quasi-static process as Q over T. And so we find NR ln of 2. You can see that the entropy change is positive, and so if we calculate the entropy change for the reverse process, then we would get minus NR ln of 2, and it would be negative. Now finally, let's do one more example with, again, a non-quasi-static process. Let's say that you have two blocks of iron, both 1 kilogram, but one is at 200 degrees Celsius and another one at 100 degrees Celsius. You put them in contact. You know that they will exchange heat with each other, and eventually they will reach thermal equilibrium, both at 150 degrees Celsius. And you also know that this is not a quasi-static process because all the steps in between are not in quasi-equilibrium. In the previous example, it was because we have a difference of pressure, and in this example, it's because we have a difference of temperature. But again, to calculate the entropy change, we can imagine another process where it would be quasi-static. For example, we could slowly remove heat from the outer block using a long rod, which would then slowly transfer the heat to the colder block. So let's calculate the entropy change for the hot block. We have delta S is equal to the integral of dq over T. And for the hot block, the initial temperature is 200 degrees Celsius, and the final temperature is 150 degrees Celsius, and dq is equal to mc dt. So we have mc ln of 423 divided by 473. Again, here make sure that you use Kelvin for the temperatures. Here in this relation, C is the specific heat of iron. And so you can do the calculation and you find minus 52.5 joule per Kelvin. So you see that the entropy of the hotter block decreases as it is cooling down. Now we can do the same for the colder block. In this case, the initial state is 100 degrees Celsius and the final state is 150 degrees Celsius. And we find that the entropy change is 59.1 joule per Kelvin. You see that the entropy of the colder block has increased. And if you combine the results to calculate the total entropy change, you see that the total entropy has increased by 6.61 joule per Kelvin. Again, you see that the total energy is the same before and after the heat exchange, right? So we cannot use the energy to explain why this process happens only in one direction. But the entropy change is positive in this direction. And if you imagine the process in reverse, where the heat would go back to the left block and create a temperature difference, then the entropy change would be negative. It would be minus 6.61 joule per Kelvin. And so let's mention here the relation between the entropy that we just introduced in this video and the second law of thermodynamics. One version of the second law of thermodynamics is simply that no process is possible in which the total entropy decreases when all systems taking part in the process are included. So in the two previous examples, the free expansion or the heat exchange, the reverse process is not possible because the entropy would decrease.